In 1913, inventor Nikola Tesla created a turbine that he claimed had an efficiency of up to 95%. However, it was forgotten by the world. This invention was remarkable, but rumors persist about whether there were conspiracies or hidden motives to hinder the widespread adoption of Tesla's turbine. Let's explore more about it in this video together. A water turbine is any rotary mechanical device that extracts energy from a flowing liquid or gas and converts it into useful work. Water wheels, water mills, or water wheels are among the simplest and most visually intuitive examples of a turbine. They harness the natural flow of rivers or streams to turn a wheel with many blades or buckets attached to its outer edge. The water wheel is attached to a horizontal shaft, and as the wheel moves, the horizontal shaft rotates, generating power used for tasks such as grinding grain, milling corn, or operating hammers for forging weapons and tools. Water turbines were developed in the 19th century and were widely used to support industrial production before the advent of today's electrical grids. Nowadays, they are primarily employed for power generation. In hydroelectric dams, water from reservoirs is directed through a pipeline system to turn the blades of a water turbine. This turbine, in turn, rotates a generator to produce electricity. In thermal power plants and nuclear power plants, turbines rotate due to high-pressure steam, while in wind farms, turbines spin with the force of the wind. They are respectively referred to as steam turbines and wind turbines. Despite the differences in turbine types, they all operate based on the principle of using blades to capture the flow of high-pressure steam or air. The kinetic and potential energy of the flowing fluid, which can be either liquid or gas, causes the blades to move and transfer rotational energy to the rotor. One of the most crucial components in a turbine can be observed to be the blades. The blades of modern turbines, especially in steam turbines, have a highly complex structure that demands cutting-edge manufacturing techniques. The average diameter of the blades of a modern wind turbine reaches up to 127.5 meters, which is longer than a soccer field. High-speed fluid flow enters one end of the turbine and exits the other end at a lower speed. The energy from this change in speed is what causes the blades to rotate. During this process, a certain amount of loss occurs. Modern multi-stage blade wind turbines today can only harness 60 to 70% of the potential and kinetic energy from the fluid flow. However, certain types of turbines, such as steam turbines and large water turbines used in power plants, can achieve efficiencies above 90%. Let's take a look at a water turbine. Once the water flows into the turbine, chaotic water swirls will form. They move in various directions, and instead of turning the blades, they may collide with each other or with the walls of the turbine, generating heat. A similar phenomenon occurs when you blend water using a blender. Tesla observed that in traditional steam turbines, steam had to be forced onto the blades for the rotor to extract energy from the steam's velocity. In optimal operating conditions, the blades needed to be arranged to minimize the angle at which steam comes into contact with their surfaces. The purpose is to create a smooth steam flow, avoiding turbulent steam streams. Turbulent steam streams are quite undesirable as they waste a portion of the useful energy that could be extracted from the system. Worse, a turbulent steam stream moving in the opposite direction can diminish the kinetic energy of the smooth steam flow entry. You are looking at the design of Tesla's turbine patented in 1913. Tesla addressed the issue of turbulent flow by creating a type of turbine without blades. The Tesla turbine uses rotating discs instead of blades. This design minimizes resistance, allowing fluid streams to follow their natural paths. Essentially, the Tesla turbine comprises a set of smooth discs with nozzles spraying fluid at the edges of the discs. When the fluid is pumped into the turbine, it follows the discs due to the viscosity and adhesive properties of the surface layer. The fluid, after transferring some of its energy, slows down and exits through exhaust pipes near the center of the discs. The motive force of the Tesla turbine is an incredibly interesting phenomenon and is no less intriguing than the brain condition called the no-slip condition, also known as the no-slip boundary condition. Let's explore the following experiment. A dark ink is pumped to the bottom of a flowing stream of water through a glass tube. While the majority of the ink is carried along by the flowing water, a small amount remains unaffected and forms a stagnant layer near the bottom. This is the phenomenon of the no-slip condition. Upon closer analysis, when a liquid flows very close to a solid surface at the interface between the liquid and the solid, the adhesive forces between the liquid molecules and the solid molecules will be greater than the cohesive forces between the liquid molecules themselves. We can say that the liquid layer has adhered to the solid surface. As a result, the velocity of the liquid layer near the solid surface decreases and becomes equal to the velocity of the solid surface, meaning zero if the solid surface is stationary. Moving away from the liquid-solid interface, the velocity of the liquid layers progressively increases until it returns to the velocity of the flowing stream. Thanks to the adhesion between the layers of fluid and between the fluid layer and the solid surface, the disk is pulled along by the flow of the fluid and accelerates rapidly. The most noticeable advantage of using disks instead of blades is that it eliminates turbulent flow, which reduces the operational efficiency of the turbine, as I analyzed above. Furthermore, the absence of turbulent flow also creates conditions for fluid molecules to move smoothly within the water layers. Each water layer slides smoothly through adjacent layers without causing disruption. Such flows are referred to as laminar flows. It sounds like Tesla created a perfect revolutionary design for water and steam turbines. So why wasn't it widely adopted? Is there some animosity toward this genius inventor in the world? The answer is no. In Tesla's time at the beginning of the 20th century, the efficiency of conventional blade turbines was very low. The reason was that they used a direct mechanical transmission system, meaning they did not employ gear pairs to adjust the transmission ratio. This severely limited the maximum speed that turbines could achieve. At the time when the Tesla turbine was introduced, marine turbines were immensely massive, consisting of dozens or even hundreds of turbine stages. However, they resulted in extremely low efficiency due to their low speed. For example, the turbine on the Titanic, launched in 1912, weighed over 400 tons, equivalent to 80 fully grown African bush elephants, yet it had a speed of only 165 revolutions per minute. To put it in perspective, the disks inside a Tesla turbine could rotate up to 35,000 revolutions per minute. Later, propeller turbines were equipped with many gears, allowing them to operate at higher speeds. However, compared to Tesla turbine, the performance of traditional turbine remains quite low. Tesla claims that the steam version of their blade turbine can achieve impressive efficiency ranging from 95 to 98%. However, researchers argue that the actual efficiency of Tesla fans is only around 60%. In the 1950s, Professor Warren Rice attempted to replicate Tesla's experiments. A gas turbine stage with some modifications compared to Tesla's patented design yielded an efficiency of approximately 36%. Despite this, it is still an impressive result, considering that by 1939, the efficiency of the most advanced propeller fan turbines had not yet exceeded 20%. So why then did the world not adopt Tesla's turbine? In a research work published in 1991, just before retirement, Professor Rice conducted an analysis of Tesla fans and a cascade flow model. He suggested that the rotor efficiency of Tesla fans using cascade flow could be very high, even exceeding 95%. However, to achieve this efficiency, the design of the fan would need to include numerous disks, and that's when problems arise. A greater number of disks implies a higher likelihood of imperfections on the surface or edges of the disks. The disks, no longer perfectly smooth, result in a less streamlined flow of the fluid, leading to increased turbulence and a rapid decline in the turbine's efficiency. Additionally, the process of supporting the turbine under load by installing a gear system with multiple gears to distribute the turbine's power to, for example, the blades of a ship's propeller, causes significant slowing down of the disks and substantially reduces the overall efficiency of the turbine. As a result, the actual efficiency of Tesla fans is only around 60 to 65%, which is equivalent to or even lower than modern multi-stage propeller fans. It falls far behind steam fans and water fans in power plants, which can easily achieve efficiencies above 90%. One can confidently conclude that the efficiency of Tesla disc fans compared to traditional propeller fans is not superior and, in some cases, even inferior. The advantage of Tesla disc fans lies in their ease of manufacturing and cost-effectiveness. If you disagree with this viewpoint, I invite you to demonstrate why these smooth discs are more complex and challenging to manufacture than traditional fan blades. Tesla turbine can also reverse their rotation, a capability that traditional fans with fixed-blade propellers cannot achieve as their blades are curved in a fixed direction.
Nice.
In addition, bladeless turbine can also operate effectively with highly viscous substances, meaning they have the ability to resist high deformation, such as molten honey, molten chocolate, or certain types of engine oils. In contrast, water, milk, and fruit juice are examples of substances with low viscosity. Since 1982, Tesla disc pumps have been introduced to the market and employed for pumping corrosive liquids with high viscosity, sensitive to the cutting force of the blade. These liquids may contain solids or be challenging to handle with conventional pumps. Perhaps the most crucial reason why the Tesla turbine could not become widespread is that Nikola Tesla was ahead of his time. He created a machine that required a type of material that his era could not provide. Even the best metallurgists of Tesla's time could not manufacture discs for the turbine that would remain unwarped during operation at speeds of 35,000 revolutions per minute. Warped discs would create chaotic flow patterns, rendering Tesla's design impractical. Looking at spinning CD discs at high speeds provides an analogy to understand the point I am trying to convey. Unfortunately, by the time metallurgical technology advanced enough to manufacture discs meeting the standards, traditional blade fans with continuously improving efficiency had already dominated for decades, and no one dared to venture replacing them with improved Tesla turbines. On the flip side, imagine in a world where Tesla disc turbines were used right from the early days. Who would have known that after 100 years of application and technological advancements, they would propel humanity forward to such an extent? In summary, the world did not reject Tesla. It's just that he created a design that was too interesting, unique, and futuristic for humanity to readily embrace. Remember to subscribe and hit the notification bell for exciting videos in the future. Thank you.